Hi guys, I welcome you to my YouTube channel, Learning Physics with IBM. My student in Pakistan asked me to record a full paper a full paper 3 of October, November. So I decided to record the paper which was recently done by my students, and I decided to use the results of one of my students just to give you a clear picture of what is required from the practical exam. So greetings from Mongolia. Greetings from the coldest capital of the world, Ulaanbaatar. And without wasting time, I would like to take you to the question paper. So this is the question paper. It is October, November 2023, Physics 9702 36. The paper is supposed to be 2 hours. It is called Paper 3 Advanced Practical Skills. You must answer on the question paper. You will need the materials and apparatus listed in the confidential instructions. So if you're a teacher, I can show you, you can just download the confidential instruction. This is the confidential instructions. So the Cambridge will send you a confidential instructions document, which comes about 2 months to the exam. And for this particular paper, I just want to show you what you really need for the exam. So students were to be provided with a 1.5 volt cell holder with the terminals. The positive terminal was clearly labeled. 3 volts DC power supply made from two 1.5 volt cells in a holder with the terminals. A resistor of 100 ohms was labeled X, of course with the component holder with the terminals. Then the following resistors were provided: 0.68 kilo ohms, 82 kilo ohms, 1.0 kilo ohms, 1.5 kilo ohms, 1.8, 2.2, 3.3, 4.7 kilo ohms. This is 1, 2, 3, 4, 5, 6, 7, 8. So the student may not use all of them because the student needs at least 6 sets of results. So he may not use all of them. I want you to also note that these are given to two significant figures. So they said labeled with its resistance value to two significant figures. So that is very important. If you label them to one significant figure, the student may lose a mark because of the teacher. Then a digital voltmeter, which is set to 0 to 20 volts. In other words, it was reading to two decimal places. So that is the multimeter you use at home, normal at school, which you were just supposed to fix to 20 volts. Just turn the multimeter to 20 volts. Then 8 connecting leads. So the rest is very simple. So that is question number 1. When I come to question number 2, I will show again the instructions. So let's look at question number 1. I said I'm going to just use my students' results just to discuss what the examiner is really interested in. Because as an examiner, I really know what the examiner really wants. So answer all questions. Use a black or dark blue pen. You may use HB pencil for any diagrams. Now at this point, I want to encourage all students that writing the results, writing anything should be by pen. And drawing a table or drawing a diagram or drawing a graph should be by pencil. Because you are free to change the diagram, you're always free to draw another graph, you're always free to delete the line or to delete the plotted points or to erase the plotted points so that you draw new ones. But writing, it's better you write by pen, and drawing should be by pencil. I think that is very important. They said do not use an erasable pen or correction fluid. Of course, correction fluid is not allowed in the examination room. If you make a mistake, for example, you wrote 25 and you want to change it, you just cross out horizontally and write above it 27. It is not really necessary to use corrective or correction fluid. Do not write on any barcodes. I think that is very obvious. And then the rest are usual instructions. So This paper has a total of 40 marks, but when it is being weighted, it becomes out of 30. When they weigh the paper, it contributes 30 out of the total mark. So in this experiment, you will investigate an electrical circuit connect the circuit as shown. So many students could find challenges in connecting this circuit because they don't follow the instructions, but this is a very simple circuit to connect. The positive terminal of the DC supply, the negative terminal of the other DC supply, the positive terminal of the voltmeter, they all make one junction. The negative terminal of the voltmeter, the other end of the resistor, the other end of the resistor, they all make another junction. Then just another wire linking the other side and the other side. It is a very simple circuit. So ensure that the polarities of the two power supplies and the voltmeter are shown in the figure. So if you don't ensure that, you will get unacceptable readings. Connect one of the labeled resistors into the component holders as resistor Y as shown. Record the resistance R of a resistor Y. So like I said, I'm using my students' results. So my student here, the first resistor she put here was 1.5 kilo ohms. So I'll record here 1.5 kilo ohms. But according to the mark scheme, the resistor to be used here, the examiner expected that a student should use resistors in the range 0.68 up to 4.7 kilo ohms. Any resistor in that range could be a value here. My student chose 1.5. The voltmeter reading should be approximately 3 volts. Of course, if your voltmeter reading is not approximately 3 volts, then you check and see if there is no problem. So for my student, the voltmeter reading was fluctuating, so she decided to take 2 readings. And as a teacher, every time your students decide to take 2 readings, encourage your students to draw a neat table like the one which my student has drawn. So because the voltmeter was not stable, it kind of fluctuated. My student decided to take a repeated measurement where she labeled in the table V1 in volts and V2 in volts. So the first reading she recorded is 2.88. Of course, the voltmeter was having a precision of 0.01, so it must record to 2 decimal places. So the next value she recorded was 2.89. Then she took the average value of the two, which she recorded to 2 decimal places. And of course, the average value of the 2.88 plus 2.89, dividing this by 2, it is approximately 2.89. So she recorded here 2.89, and the units are volts. So that is, I rounded off to 2 decimal places to maintain the precision of the voltmeter. However, if you're a student and you reach this point, you don't know how many decimal places you should record, but at least you are sure of the decimal places of the instrument. Then now here you should be very creative. If I notice that I wanted to record repeated values, but I'm not sure of how many decimal places to record, just ensure that your resultant has the same number of decimal places as those in the table. So a wise student would record the fluctuating values as 2.89 and 3.01, because this one will give you exactly 2 decimal places when you add and divide by 2, or 2.89 and 2.91. So this is now creativity. A student knows that when I add, I should get exactly 2 decimal places. So what should I record? Which values should I record in the table close to the ones I'm seeing on the display on the screen? So instead of writing 2.88 and 2.89, when you divide and you get 2.885, which confuses you, a student who is very smart would record 2.89 and 2.91 in the table, because the examiner marking the exam was not there when you were carrying out the experiment. So he will not be very sure of exactly what you saw on the screen. But at least he has an idea of where the value should be lying. So this implies this student could have written in the table values like 2.8, sorry. So this could be their V1 in volts, V2 in volts. So a student could write 2.89 and 2.91. And when this student gets the average value of V, 2.89 plus 2.91 divided by 2, this is exactly 2.90. The highest you can add is a 0 to maintain two two decimal places, volts. So this student would have been very creative rather than being attempted to write 2.885. So I'm saying this is just a by the way. This is just a by the way. Okay. So change Y and record R and V. Repeat until you have 6 sets of values of R and V. Record your results in a table. Include values of 1 over R in your table. Okay, so since we have shown that we are sure of fluctuations, we don't need to take repeated measurements here in the table. Now they always provide you with a large space for the table. I prefer that you draw a very large table so that in case you make a mistake, you don't again need to cross out to rub and draw another table. You just use the same table, but that just modify the values. So I'll draw a table. Normally I prefer that my students draw the table with a pencil, so I'll change the color of this. Because your table should be neatly closed. So I need a column for R. I will need a column for V. They said we should include 1 over R, so I will need a column for 1 over R. So for this point, prepare to produce 6 sets of results. Whether your values are correct or wrong, you have 5 free marks as long as there are 6 sets of results. So this is the row for headings. This will be the first result, the second, the third, the fourth, I should add the fifth, and I must add the sixth. Okay, so I'll just show you what my students recorded in this table. So they said we should include values of R, V, and 1 over R. So I'll change. I said when you are writing, it's better use a pen. When you are drawing, it's better use a pencil. So we need values for R. R is actually the independent variable. It's the one we are changing. Values of R have been recorded to kilo ohms. So I'll write kilo ohms. Then I'll have V. V is the dependent variable. Values of V will be recorded in volts. Then I have 1 over R. Remember, R is given in kilo ohms. So this one is going to be kilo. It is going to be per kilo ohm. You can write it like that. Per kilo ohm. Okay, so that would be per kilo ohm. So these are my students' results. So she started with 0. She didn't include what was recorded previously, the 1.5 kilo ohms. So she started with 0.82. Then she recorded the value of V as 2.67. When you carry out the experiment, don't expect to get exactly the same results. So this is just acting as a guide. Then this she got 1.2. Remember, you must when you get 1 over R, you must ensure that you have the same number of significant figures as R. So here R is to 2 significant figures, 1, 2. So here it should also be at least 2 significant figures. It can be more, but note the effect of increasing number of significant figures. The more significant figures you have, the harder it becomes to plot. So it's better you maintain the same number of significant figures. Then she also used 1.0. Those are 2 significant figures. She got V as 2.76. And of course, 1 divided by 1 is 1.0 to maintain the same number of significant figures. Then she used 1.8, which gave her 2.95 volts. And then she got 1 over 1.8, which was 0.56. 2 significant figures because R is 2 significant figures. Then she used 2.2 kilo ohms, which gave her 3.00, which when she got 1 over 2.2, she got 0.45. Then she used 3.3, which gave her 3.06. And when she pressed 1 over 3.3, she got 0.30. Then she used 4.7, and when she checked the voltmeter, it was reading 3.12, and she got 1 over 4.7, which is 0.21. So me as an examiner, I will just check the column for, the only thing I can check is the number of decimal places for V. Is it 2? Because the confidential instructions wants the results to be recorded to 2 decimal places. Reading up to 0.01, it means the values of V should be 2 decimal places. So I check V values, they are to 2 decimal places. Of course, this student has, if this student already has 6 sets of results, whether they are correct or they are wrong, this student will have B5. I'll give this student B5 for having 6 sets of results, whether they are correct or they are wrong. As an examiner, when I check the column headings, they are correct, I'll give the student a B1. As an examiner, I check the column for V to be to 2 decimal places, I'll give the student another B1. As an examiner, I now check significant figures and see if this student rounded off correctly, so I'll have to open my calculator. The first value of 1 over R is 1 divided by 0.82. So 1.2 to 2 significant figures, that is correct. The second one is 1 divided by 1.0 divided by 1.0, that is automatically correct. The third one is 1.8, 1 divided by 1.8. So this is 0.5 recurring, which rounds off to 0.56. That is also correct. I'll also check 1 divided by 2.2, which is 0.45454545. So when she rounds off to 0.45, that is also correct. If she rounds off to 0.46, that would be wrong because it is 0.454545. Then I'll check 1 divided by 3.3. So she gets 0.303030. So that means that is also correct. And I'll also check 1 divided by 4.7, which is 0.2127. So that rounds up 0.21. So because the number of significant figures is correct, this student will get another mark. So those are already 8 out of 10. Then I check consistency. Consistency means either all values are increasing or decreasing, not a mix-up. So we can see that as R increases for this student, V is also increasing for this student. So this student is consistent, so that is a B1 mark. Then because this student has calculated 1 over R correctly, I'll add this student a B1 mark. So this student gets 10 marks in total because these are always 10 free marks. So the next thing is to plot a graph of V on the y-axis against 1 over R on the x-axis. So this is where the student told me she finds a lot of challenges in plotting this graph. First of all, choosing a scale. Secondly, how does the graph really have to be plotted? So I'll take you to the grid straight away. If you're a student, I want you to make this part of you that the first thing you need to do always when you get the graph paper, or when you go to the graph paper, is to begin by drawing the axes along the edges of the grid. So I'm putting here the axes. I think I need to increase the thickness. Okay, that is the y-axis. And I'll also draw the x-axis. My axes may not be accurate because I'm drawing on a computer. Okay, you can draw better axes on your grid. So that's how the axes should look like. The examiner only allows if marks are put after every 10 small squares. Do not put a mark at more than 10 small squares. You will lose a mark. So put a mark after every 10 small squares. Of course, this is the origin. I've put these ones because I must show the origins. So on the x-axis, I put 8 marks. On the y-axis, from the origin, I have 1, 2, 3, 4, 5, 6, 7, And this is so far. 7, 8, 9, 10, 11, and 12. And my axis has gone off. Okay, so on the y-axis you have 12 marks. On the x-axis you have 8 marks. So we have to label the axes. We are plotting a graph of v on the y-axis against 1 over r. So I will change the color to blue. So on the y-axis I have v. So you label v the way you labeled in the table, v in volts against 1 over r. So on the x-axis I have 1 over r. So I'll write here 1 over r, and the units are kilo ohms per kilo ohm. Okay, now I go to the table and choose a scale. Before I choose a scale, I must look at the table and find the origin. So what should be the origin on the y-axis and on the x-axis? To choose the origin, look at the smallest value in that column. For example, on the x-axis, the smallest is 0.21. So the origin can be a value which is slightly below 0.21. Because 0.21 is close to 0, I can even take 0 as the origin on the x-axis. It may not be the origin on the y-axis. So I'm taking the origin to be a value slightly below 0.21, which is 0. So I'll write here 0.00. Then on the y-axis, let's check. To find the origin, we need a value slightly below the smallest. Now the smallest value here is 2.67. So I can take a value slightly below 2.67, which could be 2.6. I could take the origin on the vertical to be 2.6. So let this be 2.60. So I have chosen the origin. The next thing I'm going to do is to choose the scale. Let me reduce the thickness. So I'm going to choose the scale. To choose the scale, I look at the y-axis. So on the y-axis, for the y-axis, the highest value is 3.12 minus the origin, which is 2.60. On the y, I have 12 marks, so I will divide by 12. So let's check. 3.12 minus my origin, which is 2.6, divide by 12. So you notice that when I press the calculator, this gives me 0.0433 recurring. But your teacher must have told you that the scale should be related to 1, 2, 2.5, and 5. The scale should be related to this. So it means the nearest number here, which is related to n of this, is going to be 0.05. So the scale on the y-axis is going to be approximately 0.05. That's on the y-axis. Then on the x-axis, let me do it here, x-axis. On the x-axis, the highest value on the x-axis is 1.2. So I'll say the highest, which is 1.2, minus the origin, which is 0.0, divide by 8. There are 8 marks on the x-axis. So 1.2 minus 0, divide by 8. So that is 0.15. But remember, I said the scale should be related to 1, 2, 2.5, and 5. So this gives me 0.15. So I must round off this to a number related to 1, 2, 2.5, and 5. So the next number here is going to be 0.2. So it means this is going to be approximately 0.20. So the scale on the x-axis is 0.20, and on the y-axis is 0.05. So we now go and put those values here. So the next value here is going to be 0.20, followed by 0.40, 0.60, 0.80, 0. Sorry, this is 1.0, 1.00, 1.20, 1.40, and 1.60. Then on the vertical it was 0.005. So I will go on adding 0.05. So this will be 2.65. This will be 2.70, 2.75, 2.80, 2.85, 2.90, 2.95, 3.00, 3.05, 3.10, 3.15, and lastly it is 3.20. Okay, so this scale is going to give you the best graph ever because it is making the graph to be bigger. The graph should always cover more than half of the grid, more than half on the x-axis and more than half on the y-axis. Should never be less than half. You will lose a mark for that. Okay, let's now plot the points. I'll just write the points on paper so that I don't always come up to check. So 0.2.67, 1.2, 2.76, 1.0, 2.95, 0.56, 3.00, 0.45, 3.06, 0.30, 3.12, 0.21. Okay, so I have them on paper. I can now just plot. So my first point is 2.67 against 1.2. So I'm looking for 1.2. 1.2 is here and 2.67. So I have to use my scale very carefully. One small box. Remember, one small box on the vertical. On the y, one small box is 0.05 divided by 10, 0.005. 0.005, that is one small box. So how many boxes do I need to add on 2.65 to reach 2.67? So this is 2, if I add one box, that is 2.655. If I add another box, this is 2.656, 2.6. Okay, I'll just calculate. I want to plot 2.67 by adding boxes to 2.65. So I'll divide this by the scale, 0.00, the value of one small box. So I'm going to add 4 small squares to reach 2.67. So this is 1, 2, 3, 4. So this is going to be 2.67. So I'll put a cross and a small circle to make my point visible. Okay. Then the next point is 1.0 against 2.76. 1.0 against 2.76. So how do I get 2.76 from 2.75? So I will get my calculator. 2.76 minus 2.75. I divide this by the scale, which is 0.005. The scale is that when I talk about the scale, I'm meaning the representation of one small square. So those are 2 small squares. So I'll add 2 small squares on 2.75 to reach 2.76. So this is the point. Okay. Then the next is 0.56, and it corresponds to 0.95. 0.56. I have again to check the scale on the x-axis. If 10 small square is 0.2, then 1 small square is 0.2 divided by 10, so it is 0.02. So how many small squares should I add to 0.4 to get 0.4, 0.56? So 0.56 minus 0.4. I divide this by the scale, 0.02. Those are 8 small squares. To reach 0.56, I must get 8 small squares. So 8 small squares. Then to get 2.95, I think 2.95 is there. So I need 8 small squares from this. 1, 2, 3, 4, 5, 6, 7, 8. So this is the point I'm sketching. Okay. Then next, I have 0.45 against 3.0. 0.45, how many small squares are those? 0.45 minus 0.4. I divide by the scale on the x-axis, which is 0.02. Those are 2.5. So 2.5, 2.5. So 3, 1, 2.5. So this is the point. Okay. Then I have the next value is 0.3. Of course, 0.3 is just in the middle of 0.1 and 0.4, but it's against 3.06. It's against 3.06. So I have 3.05 is here. I'm looking for 3.06, so I'll say 3.06 minus 3.05. Divide by the scale on the vertical, which is 0.005. Those are 2 boxes. So I'm going to add 2 boxes, 1, 2. So this is the point. The next is, the last one is 0.21 against 3.12. Remember, each box on the x-axis, each small box is 0.02. So 0.21 is just in the middle of that small box. But it's against 3.12. So 3.12, I must add how many boxes? 3.12 minus 3.1. Divide by the scale on the vertical, which is 0.005. So I should add 4 boxes to reach 3.12. So I have 1, 2, 3, 4. 1, 2, 3, 4. So the point is going to be here, in the middle of this box. So that is my last point. So these are my points. You don't need to force them to be on a perfect straight line. Now the problem is drawing the line of best fit. So I have to minimize this so that it fits on one page. So it is going to be very small. Because there's no way I will make a judgment when I have points which are not, when the points are not fitting on the same page. So now they are fitting on the same page. So to draw the line of best fit, you must balance your points. If you notice that there is a point which is far away from the rest of the points, or which cannot be brought on the line, just label it anomalous. But if you see all your points are very close to the line, you don't need to label anything anomalous. So let me try to judge. You balance the points. You make sure at least if you leave a few points above the line, there should also be a few points below the line. That's what I mean by balancing. Let me try out this one and see if it works. So this is 1, 2, 3. Okay, I have to adjust this line. I have to rotate it further to the bottom. No, I still have to rotate it anti-clockwise. I made a mistake by passing the pencil twice. I must pass the pencil once. It was a very good line, but I passed the pencil twice, which distorted the line. This is still not good because I see 3 points almost on one side. So I have to change this again. I want you to notice how much time I'm taking to draw the line of best fit. Because to make it perfect, you must try several attempts. If you're on a paper, it is easy to make a judgment. Because I'm drawing on a computer, it is hard to make a judgment. Yes, I think this is good enough. If I try to expand this, so I can see one point is far away from the line, so I'll just label it anomalous. So look at my line of best fit. I have 1, 2, 3, 4 points on the line, and I can consider this. If you draw if you draw on a paper, this 5th point could also be on the line. Now I have a choice. I can say this point is anomalous. Sorry about this. I can label this anomalous. I can say this is anomalous because I'm seeing it is slightly far from the rest of the pattern. So I'll say this is anomalous. And if I label one point anomalous, I will not be penalized at all because I'm allowed one anomalous point. So this is going to be my line of best fit. At least it is not the best, but it is good enough. So the next thing I'm going to do, it is not a perfect line because I'm drawing on a computer. So you should be able to draw a better line than mine. You should be able to draw a better line than mine. The next thing I'm going to do is to draw the triangle because I've finished to draw the line of best fit. I've finished to plot the graph. And then the next thing is to determine the gradient and y-intercept. So of course, to determine the gradient, I must draw the triangle. So for the triangle, I have to choose 2 points. I have to choose 2 points. Okay, I will use blue for the triangle so that is visible. So I'll choose 2 clear points. For example, this point here. And I will draw a triangle using dotted. The triangle should be big enough, covering more than half of the length of the hypotenuse. The hypotenuse should be more than half of the length of the line. So I'm still drawing a bigger triangle. So I'm choosing another point at the bottom. It's better you choose a point where the grid lines perfectly cross so that you don't need to estimate. For example, I'm taking this point here. Okay. So this is my triangle. I hope it is visible to everyone. That is my triangle. Your triangle should be visible. You can pass the pencil there twice to make it visible. So having drawn the triangle, if you want, you can write out these points, but it's not necessary. I can write the point here. Remember the scale on the x-axis, each box is 0.02, so this is going to be 1.22 on the x-axis, and on the y-axis, remember on the vertical axis, each box is 0.005. So this is, if I add two boxes, that's like adding 0.01. So this is going to be 2.6. I think that is 2.6. Let me check. You have 2 times 0.005 plus 2.65. So it is 2.66. Okay. It's not necessary to write this here, but if you want, you can write it there. Then you come here. At this point here, you have on, I think this is 0.2. Yes. On the x-axis, it is 0.20. Then on the y-axis, remember on the y-axis, each box is 0.005. So you have one box which is 0.005 plus 3.10. So to be very sure, it is 3.105. 3.105. Okay, so now it is easier for me to find a gradient. This is going to be x1 and y1. This is going to be x2 and y2. So let's find the gradient. So I'll tell the examiner that the gradient, which of course I know it is change in the y values over change in the x values, should be equal to, let me see, y2 and yx1, 2.66 and 1.22. So y2 is 2.66 and 1.22. So those are the y2 and x2. Then y1 and x1, we have 3.10, 105 and 0.2. So the denominator I have 0.2 and this is 3.105. So I'll just check with my calculator. So 2.66 minus 3.105 divide by 1.22 minus 0.20. So this is giving me negative 0.4, negative 0.436. I'll just take 0.436. That is the gradient. Of course, when you look at the graph, you notice that should be negative. Then the y-intercept, of course, from y equals to mx plus c. So the y-intercept is c. So I'll say c equals to the y value. I'll just take the same values that I took for the gradient. I'll take 1.22 for x and 2.66 for y. So I'll say this is 2.66 for y minus the gradient, which is negative 0.436 times the x value, which is 1.22. I'm just making c the subject. That's why you see it is minus, but the gradient itself is negative. So this is the gradient. This is the x coordinate. This is the y coordinate. So I'll just check with my calculator. 2.66 minus negative 0.436 times 1.22. So I'm getting 3.192 if I want. So I have, this is 3.192. So the gradient is going to be negative 0.192. 3.436, and the y-intercept is going to be 3.192. Okay, so these are for the gradient. These are exactly my own values. They are not for the student. Of course, the student has a different value because of the plotting and the line of base fit being slightly different, since for them they were drawing on the question paper and I'm drawing on the computer. You don't expect to get this exactly the same results. This is just a guide to show you that your results should be around there. Okay, so that is the graph. Then the last part of the question, which normally confuses students, is this one here, which they normally again go ahead and calculate unnecessarily. It is suggested that the quantities V and R are related by the equation V equals to A over R plus B, where A and B are constants. Using your answers in C Roman 3, determine the values of A and B. So when you just look at this equation, V is going to be equal to A times 1 over R plus B. So when I compare this with Y equals to MX plus C. So you will notice if I'll just change the color here, we just compare on the y-axis of the graph, I plotted V. On the x-axis of the graph, I plotted the 1 over R. So it means the gradient M stands for the gradient. So the gradient is going to be A. And then the y-intercept, which is C, is going to be B. So where there is B, I'll put there the y-intercept. Where there is A, I'll put there the gradient. And what was my gradient? So from C, my gradient is negative 0.436 and the y-intercept is 3.192. So here I'll have a negative 0.436 and this was 3.192. Now they say we always forget this part of the question which says give appropriate units. So note that A is the gradient. So you have to go back and check what are the units of the gradient. On the y-axis, you have V in volts. On the y-axis, you have volts. On the x-axis, you have per kilo ohms. Per kilo ohms, which is the same as V. When per kilo ohms goes up, it becomes kilo ohms. The per minus 1 goes off when you get the reciprocal. So the units of the gradient will be kilo ohms, volts, or whatever order. It is multiplication of units. So it is volts, kilo ohms, volts, and so on and so forth. The order doesn't matter. Then the y-intercept, of course, the y-intercept is for the y-axis. So this is automatically volts. The y-intercept is automatically volts. So my student got 20 out of 20 in this question because she's always very careful, but she did not get the same answers as me. So that is fine. So that is question number 1. Next, I'll take you to question number 2. Question number 2, we shall begin with the apparatus required for question number 2. For the teacher, these are for the teacher preparing the exam, or you can ask for the apparatus from the teacher. You needed a stand of 1 meter, at least 1 meter, boss and clamp, 5 identical long thin rubber bands, each of approximate circumference 28 centimeters, and cross-sectional area 1 millimeter by 1.5, a stopwatch of 0.1 seconds or better. When they say 0.1 seconds, it is measured in 1 decimal place or more than 1 decimal place. That's why they say or better. A meter ruler, 250-gram slotted masses. They always tell you they give you more details. 100-gram slotted mass, the string, clip or bulldog clip, 10 A4 sheets of paper. So as a teacher, you are supposed to prepare this for the students. As a teacher, you are supposed to prepare this for the students so that they just perform the experiment. So these are the materials. The confidential instructions are specifically for the teacher to read it through and organize the practical. So I'll just take you through the results of my students and just to give emphasis on how you have to present your results. Okay. So question number 2, in this experiment, you will investigate the properties of linked rubber bands. You are provided with the two elastic strings made from linked rubber bands. The longer one is made from 3 rubber bands and the shorter one is made from 2 rubber bands. Each string has a 50-gram mass attached to one end. Measure and record the unstretched length L0 of the longer elastic band, the longer. So these are elastic bands. They can never be straight on the Vita ruler. Remember, when you're answering question number 2, you should be thinking and noting the most likely sources of uncertainty in this question. So it's very important you read it slowly as you master or as you note what is most likely going to cause an uncertainty. So in measuring the length of this rubber band, there is no way it can be straight on the ruler. So there's a limitation here in measuring L or L0. So my student decided to take 2 measurements. By the way, if you are not very sure of how many measurements you should take for the same, how many attempts you should take for the same measurement, it's better you just take 2 because you will not be penalized for repeating a measurement. So my student decided to take 2 measurements because the band was not straight on the ruler, so it's also hard to unfold the band on the ruler without stretching it. So this could change or this could fluctuate the length L0. So she took the first attempt L0 in centimeters, the second attempt L0 in centimeters. The first value she obtained is 42.1 and she got 42.2. So she got the average of these two and rounded off to 1 decimal place. So her average is 42.2. Like I told you, if you are not sure of how to write this, then ensure that when you add, you choose 2 values. And when you add, they give you exactly 1 decimal place because any measurement from the ruler should be recorded to 1 decimal place. So she could also have recorded 42.1 and 42.1. The idea is to show that you repeated the measurement. Okay. Assemble the apparatus as shown using the longer elastic band, the longer elastic string, and with a clip approximately 40 centimeters above the pad of the paper. So the setup is like that. The setup is like that. The distance between the bottom of the 50-gram mass and the pad is D. Adjust the boss until D is approximately 2 centimeters. So they adjust until D was approximately 2 centimeters. So measure and record this. So D should be very close to 2 centimeters. But remember, any measurement from the ruler in centimeters is to 1 decimal place. So my student again did a repeated measurement. So she drew a nice table. You can always draw a nice table with a ruler. So she got the first attempt and repeated for the second attempt. So she got 2.1, repeated again to check, and she got 2.1. So she recorded D as the average, which is 2.1 in centimeters. Remove the 100-gram mass from the elastic string as shown. So she removed the 100-gram mass. Measure and record the distance D0 between the bottom of the 50-gram mass and the pad. So she measured, but she took 2 measurements. First attempt, so she always draws a table. This is an A-star student. She's one of the top students in my class, so she's always very organized. So she did the first attempt in centimeters, and she showed a repeat of a measurement in centimeters. So the first attempt she measured and got 6.3. Then she repeated and got approximately 6.4. So she took the average, but had to record to one decimal place. So she recorded this as 6.4 centimeters. Using your hand, raise the 50-gram mass until the bottom of the mass is level with the bottom of the clip as shown. So you raise this, release the mass, and just watch and listen it to see if it just touches the pad. If it doesn't just touch the pad, change the position of the clip and repeat the process. Continue until the mass just touches the pad. So the stopwatch was not necessary in this question. Measure and record the vertical height, h, of the bottom of the clip above the pad as shown in the figure. So when it just touches. So she did this. She did the first attempt, h in centimeters. She repeated the measurement, h in centimeters. So you can draw a nice table. The first attempt, she got 23.4. She repeated, she got 23.5. And she took the average, h, to be 23.5 to one decimal place because it's in centimeters. Then estimate the percentage uncertainty in your value of h. Show your working. So this student will easily get the percentage uncertainty because she has taken repeated measurements. If you have repeated measurements that are different, then the absolute uncertainty is always half of the range. So this student wrote that the absolute uncertainty equals to half of the range, which is a half of the highest in the table, which is 23.5 minus 23.4. That is half of the range. So which gives 23.5 minus 23.4 divided by 2, that is 0.05. 0.05. So it means the percentage uncertainty in H is going to be the absolute, which is 0.05, divided by the value of H, which is 23.5 times 100 to make it percentage. So that one divided by 23.5, then times 100. And she got 0.213%. So she wrote here 0.213%. But that is method one. Suppose you took repeated measurements and the values are the same. There's a possibility of having 23.4 and 23.4. Percentage uncertainty of 0% is not acceptable. So suppose the values are the same, then method 2 should apply. Method 2. You must be able to estimate the absolute uncertainty of the instrument. So in measuring H, you expect to an uncertainty at the bottom if you have a ruler here. You are reading the ruler at this point, there's an uncertainty here. You're reading the ruler at this point, there's another uncertainty here. The hand cannot remain still. You cannot be sure if the ruler is perfectly vertical. Those are all uncertainties, they are accumulating. The smallest uncertainty on a ruler is approximately 0.1 centimeters or 1 millimeter, the smallest division. So since there's an uncertainty in looking at the bottom, there's an uncertainty in looking at the top, there is an uncertainty in ensure if you are not sure if the ruler is vertical when you are taking the measurement, you're actually not, the hand is also shaking. That means the absolute uncertainty in the ruler should be higher than 0.1 centimeter. So the absolute should be between, the absolute in H is between 0.3 centimeters to around 0.5 centimeters. Any value in that range. For example, I'll take 0.4 centimeters. So I will tell the examiner that the absolute in H is 0.4 centimeters. Then the percentage in H is going to be 0.4 divided by, if I have 23.5 or 23.5 as the value, I'll say 23.5 then times 100. Of course, the answers do not need to be the same. The examiner marks the method, not the answer. 0.4 divided by 23.5 times 100. So this will be 1.7%. I want you to note that if you're not sure of the absolute uncertainty in the instrument, it's always better you just have repeated measurements so that the absolute uncertainty is half of the range. The answers will never be the same, but the examiner is not interested in the answer, he's interested in the method. I hope I've made that very clear. Using your hand, pull the 50-gram mass down until it is just touching the pad as shown in the figure. Then measure L max. Measure L max. Measure and record L max of the elastic string. So my student measured from the top to the papers and subtracted the diameter of the mass, so she got approximately 49.9 centimeters. So like I said, if you're doing this practical, don't expect to get exactly the same answer. These are just guiding answers. But your answers will be around the same value if you follow, if the apparatus are assembled correctly. So, like I said, my student measured from the top to the table or to the papers, and then she measured the diameter of the mass, and then she just subtracted. But you could still measure from the top up to approximately where the string stops. You could also carry out this twice. You could draw a neat table. So what has happened to my pen? So you could still draw a table here and take the measurements twice because you are holding the ruler in your hands. So you could still draw a table, but she didn't draw that table, which does not affect the results. You could still draw a table here. You measure L max for the first attempt. You repeat and measure L max for the second attempt. You're not penalized for repeating a measurement at all. But sometimes when the repeated measurement is necessary and you have not done it, then it means there you lose a mark. You don't lose a mark for repeating a measurement, but if a measurement is to be repeated and you didn't repeat it, you would lose a mark. Repeat A, B, C, Roman 1, and C, Roman 3 using the shorter elastic string. So I will just show the results she obtained for this part for the shorter string. For the first one, she drew a nice table. I'm drawing this with a free hand, but you should draw with a ruler so that it looks very neat. So for L naught in centimeters, she did 2 attempts. So she did 28.5 and she got 28.4. The average value she recorded here is 28.5 to 1 decimal place. Then for D, she did it twice. So D first attempt, D second attempt, she first got 2.3, then 2.4, and her average is 2.4 to 1 decimal place. Then she also did two attempts for D naught. This is for the shorter string. D note first attempt, D note second attempt. So she got 5.1 and 5.1, which gave her 5.1. And then lastly, she also measured H. She did 2 attempts. H in centimeters first attempt, H in centimeters second attempt. So she got 22.3 and 22.5. So she got the average of this, which is 22.4. Then she measured L max. She did this just once and she got 34.6. Of course, the second L max should be shorter than the first L max. So those are the values. But I said she could also have done this twice, but it wasn't very necessary. She could also have done this twice for the first attempt in centimeters, then the second attempt in centimeters. You could do that twice. Yeah, so those are the values for the shorter string. The next part of the question is always about calculating the constants. So I always encourage my students to make the constant the subject in this case. So we make C the subject. So C is going to be L max minus L naught. This is squared divided by H into D naught minus D. You don't need to break down the expression so much. So the first constant, L max, of course, the first one. For the longer one, L max, I think it was 49.9 minus L naught, which was 42.2. And this is squared divided by H. H is, what was her first H? $23.5. So here she has 23.5, and then D naught, her D naught was 6.4 minus 2.1. So you can follow through if you have carried out the experiment. So I had to just check her answers. 49.9 minus 42.2, but this should be squared, divide by 23.5, 6.4 minus 2.1. So this gives 0.5, 0.58, 0.58. I can write 0.587. I'll tell you why I write 0.587. I can't write 0.6. Then C2, our C2 L max was 34.6. L naught was 28.5, but this had to be squared, divide by her value of H was 22.4, the second value, into D naught was 5.1 minus 2.4. So I had to check her values using my calculator. 34.6 minus 28.5, this is squared, divide by 22.4, 5.1 minus 2.4. and this is 0.6. I want three significant figures, 0.615. Okay, so the values that I expected her to get here were 0.587 and 0.615. Unfortunately, she did not square. Her values were fine, but she didn't square to get a constant. Then this question is always the same. Justify the number of significant figures that you have given for your values of C. Why have you given three significant figures? So the justification should always rely on the raw data. The raw data we have here, we have L max minus L naught, D naught minus D, and we have H. So you have to mention the number of significant figures for each of those. So we can say since L max minus L naught, how many significant figures are those? L max minus L naught, those are 3. Then H, or let me first start with the D naught minus D. Since L naught minus L max minus L naught is to 3, let's say it is to 3. Is to 3 significant okay, then H, the values of H I see to 3 significant figures. H to 3 significant figures. Then let's check D naught minus D, and D naught minus D to how many are those? D naught, these are 2, these are 2, and D naught minus D to 2 significant figures. So the smallest number of significant figures used in the data given is 2 significant figures. So it means C should not have less than 2 significant figures. So I'll say to maintain accuracy, C should be to at least 2. The minimum should be 2, so it can be more than 2. C should be to at least 2 significant So when I say at least 2 significant figures, it means I'm giving myself an allowance to have more than 2. That's why I've written 3 significant figures here. Okay. It is suggested that the percentage uncertainty in the values of C is 15%. Using the uncertainty, explain whether your results support the relationship. So I'll just find the percentage difference in C values. So I'll say percentage difference in C values. Percentage difference in C values is going to be, I can say the highest 0.615 minus the lowest 0.587. Then I can divide by the highest, or you can divide by the average. So I'll divide this by 0.615 times 100%. You can divide by the highest or by the average. So 0.615 minus 0.587 divide by 0.615 times 100. So this gives me 4.6%. 4.6%. So this student had got the best results, but because she didn't square, she she got a contradiction, which is fine. The examiner will not penalize her for her argument based on her results. So I will say since the percentage difference in C values is less, because 4.6 is less than 15, so it is less than 15%. So we can say C is a constant. C can be considered a constant. C can be considered a constant, and the relationship is supported. So because my student did not square her values of C, she ended up getting the contradiction, but still she just loses the mark for not squaring, but she does not lose the rest of the marks because her contradiction matches with what she recorded as her C values. So since the percentage difference in C value is less than 15%, C can be considered a constant and the relationship is supported. For my student, her percentage difference was above 15%. So she said, since the percentage difference in C values is greater than 15%, C cannot be considered constant and the relationship is not supported. That is according to my student whose results I used at the start. Okay. Then the last part of the question is the same. 4 sources of uncertainties or limitations of the procedure for this experiment. For any uncertainty in measurement that you describe, you should state the quantity being measured. Now, this is where we make mistakes. Many times we write the correct limitation, but we don't include the quantity which was being measured. So number one, we took only 2 measurements to obtain 2 C values, which means 2 readings are not enough to draw a valid conclusion. So that would be the first limitation. 2 readings are not enough to draw a valid conclusion. So how do we solve this? You can take more readings and plot a graph. Take more readings, obtain more K values, and compare them. So I'll say take more readings, and plot a graph. Or you could say take more readings, obtain more C values, and compare them. So instead of comparing only 2 C values, how about if you have more C values and compare them? Okay. Then the next one, we measure the L naught, that is the length of the string, and of course the string is not hard. It is hard not to stretch the string when measuring L, so it is difficult to measure L naught without stretching without not stretch or without stretching the string. So I would say difficult to measure L naught. Difficult to measure L naught without stretching the string. It is difficult to measure L naught. So you must also always state the quantity being measured. So it is difficult to measure L naught without stretching the string, or it is hard to make the string straight, or difficult to measure L naught since it is hard to get the string straight. Since it's hard to get the string straight without stretching it. So this is the quantity being measured L naught, and the reason is without stretching the string, or since it's hard to get the string straight. That is the reason for the uncertainty. So how would I solve this? You would tape the string to the bench, or any other method that of fixing the string to one end, or fix the string to one end. Fix one end of the string to the bench. Fix one end of the string to the bench using, you can use tape. Okay, that would help to minimize that. Then the third one could be a measure. I think there was a problem in measuring D, because when you hold D is, what was D? Let me first go back here. There was a problem in measuring D. Okay, of course, if I say D, I don't again mention. Okay, I can still mention H. There's no problem with that. But it's the same. It is almost the same. So difficult to measure D due to parallax error. The 100-gram mass was falling off. Some student, I was seeing that in the exam. So difficult. So this is the third one. Difficult to measure D due to parallax. Or you would do same, the 100-gram mass falls off. Or the ruler moves, when you bring the ruler close, it moves the string. Or the rule moves the string when brought close. The attempt of measuring D when bring the ruler close to the string, it moves the string. Or because you are holding the ruler and you are leaving a gap between the object and the ruler, there is parallax error. As you bring the ruler close to the mass, you may hit the mass and the mass falls off. So all those were affecting measuring D. And how would you solve this? Instead, you would use, if you use the bigger 100-gram mass, which you were always hitting, you would use a mass which has the same size the same diameter, let me say diameter as the 50-gram mass. So this would help to minimize knocking off the bigger mass every time you try to bring the ruler close. So you could use a smaller 100-gram mass, use a smaller 100-gram mass. When you look at the diagram, the 100-gram mass was bigger than the 50-gram masses, the 50-gram mass at the bottom. So imagine if you would choose a 100-gram mass which has the same diameter as the 50-gram masses. So you would minimize that problem of the mass falling off. Or you would say um, um, use a mirror scale behind the 50-gram mass. You could put a mirror scale behind the 50-gram mass so that you just look at the mirror. Or mirror the scale behind the 50-gram mass. You would mirror the scale behind, you get a mirror and you mirror the scale behind the 50-gram mass so that you avoid parallax. Of course, avoiding parallax means the scale on the image of the scale in the ruler is just coincident with the object itself. That one will avoid parallax. Then the fourth one could be, as some students said, it is still difficult to measure. It was difficult. There was parallax error when measuring h. Of course, that was fine. You could still say parallax error when measuring d, as simple as that. So I'll just say parallax error when measuring h. Parallax error when measuring h. How do we solve that? Parallax error, that is, which line is that? Okay, I'll write it here. Parallax error when measuring h. So this could be solved by clamp, because you are measuring h while holding the ruler in your hands vertically. That is parallax. So you could clamp the ruler or clamp the rule and use pointers. So you could use a pointer to be sure of the point you are taking measurement. Use a pointer for h or even d. So that will minimize parallax error. So this could also solve d, the previous point of difficult to measure d due to parallax error. I could clamp the ruler and use a pointer for d. Then the fifth one could be, I think it was hard to judge if the mass just touches the pad. There was a problem there. Hard to judge. If the mass just touches the pad. Hard to judge if the mass just touches the pad, or you would say difficult to align the mass with a clip before release. It was really very difficult for students. Difficult to align mass with a clip before release. Okay, so this could be solved easily. Normally, one of my students, I think the best student mentioned video. Take a video with a clip next to the ruler. So video and replay, frame by frame. Video the experiment. And replay. And replay frame. Normally replay frame by frame to see if it just touches. And replay frame by frame. Or you would use a pressure pad at the bottom, or use pressure pad at the bottom, or you put a sand tray at the bottom, or use sand tray at the bottom. Or I think you would also place a microphone near the paper and display the trace on CRO. Or place microphone, because the microphone will detect the sound, the pressures. Or place microphone near the paper and display the trace on the CRO. Of course, from the CRO, you'll be able to see where it just touches, where it just hits, or it just touches the pads or the papers at the bottom. And I think we can add one more. There was a problem in measuring L max. Difficult to measure L max. Of course, still it is almost the same as H. Difficult measuring L max. Of course, I can't talk about parallax again because I've already mentioned it. But I can talk about the ruler not being steady. You can't hold the ruler in your hands steadily. So I can say difficult to measure L max. Difficult to measure L max. The reason is the rule is not steady, or the rule is unsteady. Or you would say the string may not be perfectly vertical. You're measuring H in the vertical, but the string may not really be very perfectly vertical. That's one difficult. And how would we solve that? I think this is what my student did, measuring to the bottom of the mass and then subtracting the diameter of the mass. So if you have done that, of course, in the experiment, you cannot write it here. So measure to the bottom, of the mass, or to the pad, measure to the bottom of the mass, or to the paper pad, and subtract the diameter of the mass to obtain L max, and subtract diameter of the mass to obtain all marks. Okay, so I think that is all. I've tried my level best. In case there are errors, I'm a human, I'm bound to make those errors. So you can always just write a comment. You can always criticize, I have no problem with that. I've tried my level best. So until next time, see you in another paper. Bye bye.